Hello fellow hams and YouTubers. Today we're going to have a look at my digital mode audio interface that I built for JT65, Slow Scan TV, RIDI, CW, PSK31, any of the digital modes that are out there. It's a USB audio interface, very similar to the Signal Link, which is very popular these days. Except this didn't cost $100. It can be put together for about $20 in parts. And we're going to have a good look at it here. So, audio interfaces. What are they for, and what are digital modes? How about a quick short history of digital modes and audio interfaces, and then we'll get to the DuinoVOX. Transmission of text was invented way back in 1849. Two hard-wired keyboards with a multi-wire cable between them. Early experiments led to audio transmission with two tones, a mark and space tone, and a 5-unit code called baudot. Invented in 1874 by Émile Baudot, we say baudot, but with the spelling and location being in France, I wonder if it's Baudot. On through the 1940s, big, bulky teleprinters were used to send news and other information over telephone lines. That's where the term newswire, or news coming down the wire, came from. Ham radio ops put these machines on the air with the familiar radio teletype, or RIDI mode. In recent decades, due to computers coming with built-in sound cards, hams have invented or adopted many different ways to send text, images, and other data over the air. Today, there are approximately 30 or more audio-based modes of transmission. Early computer interfacing was done directly from the computer's built-in audio connectors to the radio's mic, input, and headphone jack. Push-to-talk was accomplished by using signals from the serial port and some discrete electronic circuit to key the transmitter when those serial pins went high. Modern radios have an auxiliary port on the back. These ports have line-level audio out, audio in, and push-to-talk pins. This allows for easy connection to a computer without having to unhook your microphone or mess with the volume knob on the front. As computers lost the serial port as a standard device, a new type of computer interface started to show up. Here is a block diagram of a modern USB rig interface. In its simplest form, you have a USB-powered sound card and a VOX circuit. The VOX, or voice-operated transmit, will key the radio whenever audio is present. This eliminates the need for any separate keying connection to the computer. Some control over the VOX can be added, such as delay or hang time, introducing a slight delay before dropping the push-to-talk line. That's useful if you're sending keyboard Morse and don't want your rig chattering in and out of transmit with each dot and dash. The delay would also be useful for modes like slow scan TV or fax, where some pockets of silence will occur during the transmission. The VOX circuit can be tricky. You need to detect a low audio level and somehow short the push-to-talk line on the radio to ground. There are many circuits out there to choose from, many requiring external power of 9 or 12 volts. If you want to change their behavior, you need to fiddle around with the electronics, and it can take time. So my idea was to replace the discrete electronics with a microprocessor and control the VOX through software. These days, this can be done very easily and cheaply through a wonderful little device called the Arduino. This is the Arduino Nano, a tiny board about the length and width of your thumb. It has 13 digital input-output pins and 7 analog input pins. The Arduino is very easy to program and can be bought quite cheaply. A friend recently bought Chinese versions for only $12. Now what about the USB audio? Well, we're not going to build a USB sound card. That would be beyond the scope of this video. However, cheap USB sound dongles are widely available. Search Amazon.com for USB sound adapter, and you'll find many from a few bucks to around $10. Make sure you look for one that has a split plastic case so you can easily take it apart. You'll also need to solder a couple of wires in there to tap the 5-volt USB power and ground. Okay, let's look at the schematic for the DuinoVOX. There's not a lot of components involved. I tried to keep it as simple as possible. Starting from the left, obviously, we have the USB audio dongle that you've bought. You'll have to disassemble it and probably use an extension cable to come out of the back of the case, or find a female connector and wire it in. Once you've done that, you'll want to tap the 5 volts and the ground from the USB audio dongle. Now you'll notice that the 5 volt tap goes up to a switch labeled Vox Enable. That provides 5 volts to the rest of the circuit. The reason that I did that was I wanted to be able to turn off the Vox circuitry but still use the audio card, so I'm not going to worry about accidentally keying the radio. I can turn on the Vox when I'm ready to do some transmitting and playing around on the digital modes. Now, the headphone audio coming from the USB dongle, you'll want to either use a couple of little connectors, 1/8-inch connectors, to plug into the existing jacks, or what I did was desoldered the jacks and soldered little coaxes on in place of them so I could tap the audio out. The headphone left audio will go through R1, which is a potentiometer, and that tap from that potentiometer goes to your connector for your rig audio in, or microphone jack. The radio's audio out is going to come into the mic in on the USB dongle, obviously. Now C1 and C2, I used a couple of non-polarized capacitors because I had them available, but you should be able to use regular old electrolytics. It shouldn't matter which way the polarity is, the audio is going to pass right through. Now T1 is necessary to get a really good sensitivity. The audio coming out of the USB dongle is only about 20 to 100 millivolts peak to peak, and the Arduino can sense a voltage range of 0 to 5 volts. So I wanted to expand that audio to a DC range that could be sensed over a greater range. So T1 is basically a small amplifier. The audio is coming in, being amplified, and then D1 is rectifying it to DC. C4 is smoothing that DC out to a nice steady voltage. R6 is a bleed resistor for the capacitor, so when the audio goes away, the capacitor is bled down very quickly and the push-to-talk can be dropped. Then the rest of it's just the Arduino. All of it's done through software. The code will be posted at the bottom of the video. The audio comes in through pin A1. The software senses that, and when there is a voltage level there, it keys the push-to-talk for a specified delay. The keying is done from D13, the output pin there. I chose that one because there's an LED on top of the Arduino, and it was nice to have a visual aid while debugging the software. You could use any of the other digital pins if you wanted to. That's fine. I chose to leave it that way, so I had that nice little LED on top of the Arduino that's lighting up when the push-to-talk keys. If you had a clear plastic case you put it in, that might make a nice little visual addition. And then the keying circuit's very straightforward. R9 limits current, so we're just turning on T2, and T2 is grounding the radio's push-to-talk line. D2 is there to protect that transistor if you have a slightly older radio that perhaps uses a keying relay. You don't want those transient spikes to pop that transistor. And C5 is just a bleed resistor to bleed off any RF that might be coming in from the push-to-talk line. Now, below the Arduino, you see R7 and R8. Those are our two adjustments. We have a delay adjustment, R7, and a sensitivity adjustment, R8. Those just vary a voltage to two more of the analog pins on the Arduino, and then the software does the rest. Of note, and I put it there on the schematic, the turning the control to the left would be ground for the delay. Turning the control to the right would be ground for sensitivity. It goes in the opposite direction because sensitivity is raising a threshold for the push-to-talk to a higher level to decrease the sensitivity. So you want turning it to the left for low sensitivity to increase that voltage, and then the software will increase that threshold. So wire sensitivity counterclockwise for 5 volts, wire delay clockwise for 5 volts, and the sensitivities will work right. The rest of the discrete components, I tried to use really common values for the resistors to make it easy to find them. The transistors are any generic 2N222 switching transistor. A 2N3904, 417801 would be a Heathkit part number, any common NPN transistor. So that's basically the electronics. all the rest of the magic is done in software. Okay, here's a closer look at my build of the DuinoVOX. Okay, here is the DuinoVOX front panel. As you can see, we've got sensitivity control, the delay control, and down here is the transmit drive control. Over here is our Vox enable switch that switches power from the USB cable to the internal circuitry. On the back, we have the rig connector, which I used a 5-pin DIN, kind of like a MIDI connector. You could use any connector that you want, whatever works for your situation. The 5 pins gave me exactly the number of pins I needed, well, with a couple extra. You really only need ground, audio in, audio out, push to talk. So I use the other 2 pins as additional grounds for internal wiring. This is just an auxiliary audio I added so I could actually feed a second audio source in on demand if I needed to. You could ignore that. Here we have the USB cable coming out of a strain relief. And right next to it, I don't know if you can see that, I guess you can, that is the USB connector from the Arduino. I've got that accessible here so that I can plug into it to update or tweak the software if I need to. And that's ground there. So now we'll open it up. Okay. Inside we have the USB audio dongle I used. I just happen to have this on hand. It's kind of big, but you could use a smaller one, obviously, from Amazon. I've used thin audio coax here that I soldered in place of the headphone and microphone jacks on the audio dongle. Front panel, straightforward. Controls and everything's wired there and routed back to the board. And back here is the Arduino, the little transistor amplifier that converts and drives the audio, and the keying circuit is hiding down here in the corner. So it's a real simple bit of electronics. Up here is the audio coupling capacitors. If you want to isolate your radio from the electronics, instead of coupling capacitors, you could use a couple of 600 ohm isolation transformers. It was extra cost. I've never had a problem using capacitors, but for some older radios you might want to isolate using transformers. And the keying circuit, again, I used a simple transistor collector switch for the keying circuit, but you could use an opto isolator in place of that transistor and it would work exactly the same. So easy enough to change if you choose to. So that's the inside of it. Let's take it over, hook it up to the radio, and I'll give you a demo of it working. Okay, demo time. I have the DuinoVOX hooked up to my little Yaesu FT817. Down here on the netbook, I have FL Digi running. I'm going to be capturing its window and hopefully be able to show you what I'm doing there. And first we'll talk about how you configure it. When you plug the DuinoVOX in to your computer, its audio dongle, whichever one you chose, will show up as an audio device. And then you go into your software, FL Digi, Ham Radio Deluxe, whatever program you're running, and choose that device as your audio capture and playback. We'll do that now on FL Digi. So I'll go into Configure, and I'll go to Sound Card, and as you can see, the audio interface that I had was called a Telix, and that's what shows up in my list, Telix USB audio. So I select that for capture and for playback. Now remember from the schematic, the right-hand channel goes to the Vox circuit. I did that because FL Digi, and I'm sure other programs, have an option for right channel keying, and you can You can set a simple push-to-talk tone on the right channel if you want to use that type of keying. I just went ahead and told it to use the modem signal on both left and right channels. In WSJ-TX, there was an option for both channels for your output. So if your software should support that. You should be able to mirror the output to both the left and right channels, or use the right channel independently for a push-to-talk tone if that's the way you want to go. Either way it works. Okay, so once we've got that set, when I put FL-Digi in transmit mode, its audio is going to come through the DuinoVOX to the radio. And to test that, I've got it in CW mode because I'm going to talk about the delay. With the delay turned down, the radio is going to cut in and out of transmit with each dit and da. This is where the delay control would be useful for CW. So I'll give you an example. I will start to transmit some Morse, a series of V's, my call sign, and the word testing. And you'll see the Yaesu kicking in and out of transmit. I'm going to go ahead and zoom in on the Yaesu and the DuinoVOX. Okay, here we go. We're going to transmit. What I'm going to do is, while it's transmitting, I'm going to increase the delay control. And you'll see how that works when you're in CW mode. And you can see it's shuttering in and out of transmit. But it's still clean. You can hear it on the icon. See, I increased the delay and we're not dropping. So you could use the delay control to operate more CW. If you decreased your speed, you'd have to increase the delay. So let me drop my speed down to, let's say, 10 words a minute. And we'll send that again at the slower speed. Now you can see it's dropping out between the letters. I could increase that if I wanted to. Until we don't drop out. I could actually increase the delay to a maximum of 2 seconds. And you can see it's not dropping out at all now because we've got a 2-second hang time. So it really depends on how you want to operate, how you use that delay control. Now you can see there was 2 seconds after that last dit before it dropped out. And I'll show that here. I'm going to send an E, so we'll hear 1 dit, and then there should be a 2-second drop. There you go. So that's how the delay control can be useful if you're sending keyboard CW. If you're sending most modes, you just want to drop that delay right on down to 0. Sensitivity, it adjusts the threshold at which the audio has to exceed before the box kicks in. The reason that I put that in there, and I'm going to switch FL-Digi quickly over to use the built-in speakers. Audio. Devices, okay, playback, built-in audio. And we're going to go to a mode called throb. Where's throb? There's throb. Now if you listen, when I put throb in transmit mode, you'll hear that its volume goes up and down and up and down. Some other modes might have silence in them, like slow scan TV or facsimile, or a change in volume level. So the sensitivity control, if I put that to minimum sensitivity, is raising that threshold way up, so the audio really has to get up there before it'll kick in. And with throb, you're going to see it drop in and out of transmit mode. So let me go back here and put the sound back on the Telex, which is what the DuinoVOX has. And we'll put it into transmit mode. And you can see how it's dropping out of push to talk as the audio volume decreases. So I can increase that sensitivity to a point where that volume drop no longer takes it out of transmit. and then it drops out when the audio stops. So that's the usefulness of the sensitivity control. It depends on the mode you're operating. For most modes, I leave it about halfway. For PSK, MFSK, JT65, JT9, any of those, I leave it about halfway. And if it ever starts dropping out during transmit, I can just increase that sensitivity, which will drop that threshold down so it takes less audio to trip the Vox. That kind of flexibility is really nice to have. Having those two controls, you can adjust the Vox behavior to be just about any way that you like it for whatever mode you're operating. So that is my digital modes interface, USB interface. I hope you enjoyed the video, and if you want to build one, I certainly hope you experience a good time using it and it works well for you. The schematic, as you saw earlier in the video, is nice, big, and full screen. You could capture that screen to get it. The source code will be down below in the video description. And if you need either of those, if you can't capture it from your screen, my email is good on qrz.com. So send me an email and I'll be happy to send you the schematic as a picture and the source code, and you can build your own. So thank you for watching. If you enjoyed the video, please share. It helps me out. And have a good day. 73.